Good morning, my wonderful team. I hope you're doing great in this amazing day. As you know, we have a mandate to work in the office 5 days a week, so I appreciate you being at your desk. However, I'll be working from home as I have too many managerial things to do. But please, conform to the mandate or I'll have to take actions. Okay. Alright, team, the reason we are here this morning is because I need you to make sure our new microservice solution is performant. Can you do that?
Certainly. Could you clarify what you mean by performant?
You know, fast and efficient. It needs to perform well.
Right, but could you be more specific? Are there any particular metrics or benchmarks we should aim for? Do you have detailed non-functional requirements for us?
Just make it snappy. Users hate waiting, so it should be quick, swift, lightning, and speedy. You understand what I mean, right?
Okay, but how quick? And under what conditions? Can you clarify, please?
Look, listen team, I'm not the technical expert here. That's your job. Mine is to provide the requirements, and the requirements cannot be clearer. Just make it performant, alright? I trust you'll figure it out. Anyway, I have very important product management things to do, so I cannot explain you further. But the ask is simple. I want our microservice to be the North Star of performance, okay? So, just do it. Team, thank you and have a great day.
Okay, awesome requirements. Jack, what do we do now? How are supposed to interpret snappy and lightning in terms of technical measurable metrics?
As we always do. Let us regroup in an hour, and we can work together to determine smart non-functional requirements around performance.
Welcome. Well, if that scenario felt familiar, you're not alone. Performance is often thrown around as a vague requirement, leaving development teams struggling to define and measure it. In this video, we're going to demystify non-functional requirements related to performance for microservices and cloud-based solutions. We'll explore what performance really means in this context, how to define clear, measurable performance criteria, and metrics to achieve and maintain high performance in distributed systems. By the end, you'll have a solid understanding of how to translate, make it performant, into actionable, quantifiable goals for your team. Let us start by understanding what non-functional requirements, or NFR, are and why they're so crucial in software development. NFR define how a system should perform, rather than what it should do. They specify the quality attributes and constraints of a system, such as performance, security, and scalability. NFR are vital because they ensure that a system not only functions correctly but also meets user expectations and business needs in terms of quality and efficiency. Allow me to double-click on the differences between functional and non-functional requirements. While functional requirements describe specific behaviors or functions of a system, NFR focus on its overall characteristics and performance. For example, a functional requirement might state that a system should process orders, while an NFR would specify how quickly or securely it should do so. Now, in the context of microservices and cloud solutions, performance is a critical NFR. Indeed, these architectures often deal with distributed systems, high scalability needs, and varying loads. Ensuring optimal performance is essential for maintaining user satisfaction and delivering a competitive edge in the market. However, achieving the North Star of performance, as in our example, can be extremely costly. Let me be clear, if your requirement is to make it performant, it is not an actionable requirement your team should be working on. Instead, you should explain your product owner and product manager that performance isn't just about speed. It's about how well the entire system responds to user demands across a distributed architecture. It encompasses how quickly services process requests, how efficiently they use resources, and how well they scale under varying loads. Let's dive a little deeper into what performance means in the world of microservices and cloud computing. Performance has multiple facets: speed, scalability, efficiency, resilience, latency, and availability. Speed in microservices refers to how quickly individual services can process and respond to requests. It's a critical factor in user experience and overall system performance. Two important metrics to capture are the response time and the throughput. We'll talk more about them shortly. Second, Scalability is the system's ability to handle increased load by adding resources. It's crucial for maintaining performance as demand grows. Please check my previous tutorial where I explained the differences between horizontal scaling and vertical scaling. Then, we have efficiency, which measures how well the system utilizes available resources. It's about maximizing performance while minimizing resource consumption. Here we need to understand and measure the percentage of available resources, CPU, memory, network, being used by our service so that our service can be cost-effective, achieving optimal performance with minimal resource expenditure. Next is resilience. Resilience is another important aspect to understand. It's the system's ability to maintain performance levels despite failures. It's crucial for ensuring high availability and reliability. When it comes to resiliency, we're talking about the ability to continue operating in the event of partial system failures, as well as the self-healing capabilities to automatically recover from failures without human intervention. Please check out our most recent tutorial in which I dive into the circuit breaker design pattern. We then have latency. This is the delay between a request being sent and a response being received across services. It's particularly important in distributed systems. As a solution owner, you must be able to measure and monitor both network latency, delay caused by data traveling across the network, and processing latency, the time taken for a service to process a request. Finally, availability is the percentage of time a service is functioning and accessible during its agreed service time. You probably have heard about availability targets, which are often specified in SLAs between service providers and customers, right? By focusing on all these aspects, you can create a well-rounded approach to performance optimization in microservices architectures. Each of these areas interplays with the others, and improvements in one often lead to benefits across the entire system. For example, reducing latency can improve speed, while better efficiency can enhance scalability. A holistic approach that considers all these factors is key to building high-performing, resilient microservices systems. But let us dive even deeper into some of these non-functional requirements and talk about metrics. But before we talk further about the metrics you need to consider for each of these aspects or non-functional dimension of your system, let's be smart. Remember that our initial problem is not having clear performance requirements from our product owner. And so, as we work toward coaching our non-technical product owners on the different dimensions of non-functional requirements, we can still talk the same language when it comes to defining clear requirements for our microservices and cloud solutions, using the commonly adopted SMART criteria. Specific. The requirement clearly defines what needs to be accomplished, leaving no room for ambiguity. Measurable. The requirement includes concrete criteria for measuring progress and success. Achievable. The requirement is realistic and attainable given the available resources and constraints. Relevant. The requirement aligns with broader business goals and objectives. Time-bound. The requirement specifies a deadline or timeframe for completion. Once you agree with your product owner to ensure NFR or SMART requirements, the remaining challenge is to coach your product owner on the important metrics to use for each aspect of your NFR. And this is what we're going to talk about now. Let's expand on the metrics related to speed. Speed is, of course, a critical aspect of performance in microservices architectures. It affects user experience and system efficiency. First, we can talk about response time, which is the total time taken for a service to process a request and send back a complete response. This metric directly impacts user perception of system performance. We usually measure it in milliseconds. But, here, we need to distinguish different types of response time, with, for example, the average response time, which is the mean time across all requests. We can also measure and monitor the median response time, or P50, which is the middle value in the dataset. We also have the 90th percentile and the 95th percentile, or P90 and P95 respectively, which are used as more stringent performance targets. So, depending on your service, you'd want to use the right type of response time. Obviously, the more business critical your service is, the more stringent your target should be. Then, we have the throughput metrics, which is the number of requests a service can handle in a given time period. It's usually expressed as requests per second, or RPS, or transactions per second, or TPS. It's a very important metrics to understand because it indicates the capacity of a microservice to handle a specific load when running on single node or compute engine. And once you know the maximum throughput your service can handle when running on one node, you can better ascertain how to scale up or down your infrastructure to handle the forecasted traffic. So, as mentioned earlier, each non-functional dimension of your system interplays with the others. This means that if you're able to improve the throughput of your service, it will lead to benefits across the entire system. Now, if we put ourselves into the end user's shoes, there are other speed-related metrics that are important to measure and monitor. For example, the time to first byte, which is the time taken from the client sending a request to receiving the first byte of the response, or the time to interactive, or TTI, which the time taken for a web page to become fully interactive. And there are many more client-side metrics we could discuss here. But in the interest of time, let us move on and talk about scalability metrics. Let's start with the metrics called request rate. This is the number of requests received by a service per unit time. It's typically expressed as requests per second, RPS, requests per minute, RPM, or requests per hour, RPH. The purpose of this metrics is to help in capacity planning and resource allocation by identifying usage patterns and peak periods. It's therefore crucial for understanding the system load and its potential bottlenecks. The next metrics is the resource utilization under varying loads, including the CPU usage, which measures the percentage of CPU capacity being used. The idea is to detect when the compute engine running your service experiences a high CPU usage, so that we can scale or optimize your existing resource before observing a service degradation. Similar to the CPU usage, as part of this set of metrics, we include the memory usage, the network usage as well as the disk I/O. Let's now talk about the time taken for the system to automatically adjust resources, scale up or down, in response to changes in demand, or auto-scaling response time. This is an essential metrics to ensure your system can handle sudden spikes in traffic. It also can help optimize resource utilization and costs. But it's also important to understand that this metrics encompasses several components. The detection time, or how quickly our service recognizes the need to scale. The provisioning time, which is the time taken to add or remove resources. And finally, the warm-up time, which is the time for new resources to become fully operational. Simply put, measuring auto-scaling response time is more intricate than it appears at first glance. Last metrics I'd like to discuss here is concurrency, which is the number of simultaneous requests or operations a system can handle at a given time. This requires the ability to measure the number of concurrent users, concurrent connections, thread counts in your service, and so on. In short, the more you know about your service's ability to handle multiple requests simultaneously, the easier it is to identify early potential bottlenecks or failures in your system. It'll also help you understand and measure the elasticity of your system, or to say differently, how well your system can adapt to workload changes by provisioning and deprovisioning resources. Let's talk about efficiency. As mentioned earlier, efficiency measures how well the system utilizes the available resources. It's about maximizing performance while minimizing resource consumption. There are a few important metrics of efficiency. Resource utilization. We already talked about this set of metrics, including CPU usage, memory usage, network bandwidth usage, and disk input and output. The second set of metrics is associated with cost effectiveness. Cost per transaction measures how much we spend on infrastructure for each transaction processed. For example, if our total infrastructure cost is $10,000 per month and we handle 100,000 transactions, our cost per transaction is 10 cents. A lower cost indicates better economic efficiency, similar to getting more miles per gallon in a car. On the other hand, resource cost versus performance gain analyzes the relationship between resource allocation and performance improvement. For instance, if adding a server costs $100 per hour but significantly boosts transaction capacity, it's worth it. However, if the next server only marginally improves performance, we might hit diminishing returns. Then, we have the cache hit ratio metric, which is another key performance metric that measures the efficiency of a caching system. It represents the proportion of content requests that are successfully served from the cache, without needing to retrieve data from the original source, like a database or origin server. Calculated as the number of cache hits divided by the total number of content requests, it's typically expressed as a percentage. A higher cache hit ratio indicates better caching performance, as more requests are being served quickly from the cache. This metric is crucial for evaluating the effectiveness of caching strategies in improving system performance, reducing load on backend servers, and enhancing user experience by decreasing response times. Last, and I acknowledge that there are many other metrics of efficiency we could discuss here, let me talk about the resource elasticity. It's typically measured as the degree to which a system can scale resources up or down in response to demand fluctuations. A common metric for resource elasticity is the ratio of the change in allocated resources to the change in workload or demand. For example, if a 10% increase in workload results in a 9% increase in allocated resources, the elasticity would be 0.9. Perfect elasticity. A ratio of 1.0 means the system scales resources exactly in proportion to demand changes. Okay, we are now halfway done. But let us be resilient and we'll cross the finish line together. You see what I did here? What an intro for our next type of non-functional requirement. Resilience. Resilience metrics aim to quantify a system's ability to prepare for, withstand, and recover from disruptions. First, the fault tolerance metrics quantify a system's ability to maintain functionality and performance in the presence of faults or failures. Common fault tolerance metrics include the average time between system failures or mean time between failures. We can also measure the fault coverage, which is the percentage of potential faults that can be detected and handled by the system. Next is the metrics around self-healing capability, which is the ability to automatically detect, diagnose, and repair issues without human intervention. This typically includes metrics like the percentage of failures resolved automatically, the average time for self-healing processes to complete, and the frequency of successful self-healing actions. Third metrics are the error rate and error detection rate. The error rate is a metric that measures the frequency of errors in a system or process. Of course, a lower error rate indicates better accuracy and performance. And the error detection rate measures the system's ability to identify errors when they occur. This is expressed as the percentage of errors successfully identified by the system. The fourth metric is a great way for me to ask you to check out one of my previous tutorial videos, since it's about the number or frequency of circuit breaker activations to prevent cascading failures during a defined period of time. Next are metrics around recovery. Here, we have the recovery time objective, or RTO, which is the targeted time within which a system should be restored after a disruption. We also have the mean time to recovery, or MTTR, which is the average time to recover from failures. Last critical metric in the realm of resilience I'd like to talk about is performance degradation, which measures the degree of functionality or performance lost during a disruptive event. This metric underscores the importance of conducting comprehensive and consistent performance testing across various dimensions. Regular load testing helps assess how microservices handle expected traffic volumes, while stress testing pushes the system beyond normal operational limits to identify breaking points. Endurance testing evaluates long-term performance stability, and spike testing simulates sudden traffic surges. Ultimately, a robust performance testing strategy is essential for building resilient microservices that can withstand disruptions while minimizing performance degradation. Let's move on and talk about latency in microservices. Think of latency as the delay between asking for something and getting it. There are several types of latency we need to consider. Network latency. This is like the travel time for data. Imagine sending a letter. How long does it take to reach its destination? That's network latency. Next is processing latency. Once your request arrives, how long does it take to be handled? It's like the time a barista needs to make your coffee after you've ordered it. Then, we have the processing time. This is specifically how long a service takes to do its job, not counting travel time. It's useful for spotting if a particular service is slowing things down. Fourth metric is the inter-service communication latency. In microservices, different parts of the system talk to each other. This measures how long those conversations take. Last, let me talk about the long-tail latency, which is about those frustratingly slow responses that happen occasionally. It's like measuring how long the longest queue at the grocery store gets, even if most queues are short. Last dimension I'd like us to discuss is the concept of availability, which is the percentage of time a service is functioning and accessible during its agreed service time. Availability is a key performance indicator service owners monitor closely, as any downtime experienced by a service can have a dramatic consequence on the organization. consequences that are financial and more importantly on customer satisfaction. This metric is calculated by subtracting the total downtime from the agreed service time, dividing the result by the agreed service time, and multiplying by 100. And as you can guess, availability metrics and service level agreements, or SLA, are closely intertwined. As background information, an SLA is the contract between the service provider and its customer that defines the expected level of service, including uptime or availability. This contract is typically expressed in nines as a percentage of uptime over a given period, typically a year. The higher the number of nines, the stricter the SLA and the more challenging it is for the service provider to meet. 5 nines, or 99.999%, availability is often considered the gold standard in many industries, representing a commitment to almost continuous uptime with only about 5 minutes of downtime per year. Alright, this is it for today. We covered several types of non-functional requirements, from speed, scalability, efficiency, resilience, latency, and availability. And we went over the most important metrics in each of these dimensions. So hopefully, next time your product owner asks you and your team to make your system snappy and lightning, they will be more precise and use the appropriate terminology to express and explain what they truly need from your service to meet their business goals. I hope you enjoyed this tutorial as much as I did developing it. As always, please subscribe to the channel if you'd like to get notified when my next tutorial is published. And on that note, let's continue growing and learning every day. See you next time.